characteristic polynomial is given here. So, since the order of the polynomial is 8, there are n equal to 8 flip flops required, right. So, let us draw a shift register with 8 flip flops. So, we are going to use D flip flops to keep it simple. And these are our clock signals. Right. So, let us say this is our input, serial input and serial output. So, sometimes we can write it as serial in and serial out. So, it is a good idea to label these as 1, x, x square, x cube, x power 4, x power 5, x power 6, x power 7 and x power 8. Okay. So, what this really means is, if I give an input here, it gets delayed by 1 unit. Okay. So, this x is like a delay operator. Okay. X square means the input gets delayed by 2 time units, right. So, that is what really it means. Okay. So, when we had to sum up x to the power 8, x to the power 6, x to the power 5 and x to the power 4, remember summation really means an XOR and we can join them together. Okay. So, this is the architecture of the 8-bit LFSR. Okay. And according to Wikipedia, this LFSR is a maximal length LFSR. Which means if you start it with a seed other than 0, it will go through 2 to the power 8 minus 1 states, okay, or 255 states. Okay. So, initially we are going to put the value of seed as 25. Okay. So, 25 in decimal, let us convert it into hexadecimal. So, 25 divided by 16, right. So, that is 1 is the quotient and the remainder is 9. So, it is 16 in hexadecimal. So, if you write this in binary, it becomes 0001 and 1001. So, this is the initial value that we are going to load into the LFSR, and then the machine will begin to generate random values in the register, and it remains to be seen whether all the 255 states are getting generated, right. So, we believe that the answer to this question is 255, okay, 255, 250, not 2 to the power 55, 255 states, okay, or 2 to the power 8 minus 1 states. Okay. You can verify this in many ways, right. So, like I said last time, you could build an actual circuit using, let us say, circuit verse or something like that, right. So, we can do that, or we can also, in this example, it may not be too difficult to do something in Excel also, right. So, let us try Excel sheet. Okay. So, this is also sometimes a useful way of verifying, right. So, let us assume that this column represents the leftmost value, let us say x, right, and this is x square, x cube, x power 4, x power 5, x power 6, x power 7, and last but not the least x power 8. And remember, the seed was 19 in hexadecimal. So, 0001 and 1001, 1001, right. Now, what is the next state? So, the feedback to the last stage is as illustrated here. It is x8, x6, x5, x4. So, remember 4, 5, 6, 8 are the 4 feedbacks. So, what we have to do is we have to take the sum of x4, which is D2, right, and then there is D E, I am sorry, E2, okay, then x6 and x8. So, F2 and H2. Okay. So, these are the 4 values that are going to be XORed, and XOR is nothing but some remainder 2. Okay. So, let us try remainder 2. I believe it is remainder. Just a minute. Some D2, E2, then F2 and H2, right. So, if you only do this, you will get so this has to be remainder 2. So, we will have to write remainder. So, mod 2. Okay. So, remainder when you divide by 2. Okay. And what about this guy? This is nothing but the shifted value. So, this should become simply A2, right, and this should become B2, right, and this should become C2, this should become D2, it should become E2, and this should become F2, and this should become G2. Okay, once again, the value that gets shifted in the least significant bit is nothing but D2, E2, F2, H2, which represent the values in the 4th flop, 5th flop, 6th flop, and 8th flop, and there is a shift operation happening here. So, this is nothing but A2, okay. This will become B2, then C2, right, B2, C2, then D2, E2, F2, okay. This is F2, okay, and then last but not the least G2. So, this is the next state, okay. And in Excel, if you just select these lines and drag it below, it will give you the next state, okay. And one more time you will get another state, okay. So, if you keep dragging it, okay, you will get So, we believe it is 255 states, right. So, let us go all the way up to 255, maybe one extra. Okay. So, you can see that even Excel can help us simulate, right. After all, we are only interested in the functional verification to see whether the flip flop really, whether the LFSR really produces all the states, right. So, this may be more than enough for us to go ahead and test, right. So, let us go back to the beginning. Okay. So, let us write down the state value, okay, as a maybe a decimal number. Okay. So, how do you find a decimal value? You multiply the relative weights of these are 2 to the power 0, 2 to the power 1, 2 to the power 2, etc. So, let us write down the state value as A2 multiplied by 128, because it is 2 to the power 7, plus B2 multiplied by 64, plus C2 multiplied by 32, plus D2 multiplied by 16, plus E2 multiplied by 8, plus F2 multiplied by 4, plus G2 multiplied by 2, and last but not the least is H2 multiplied by 1, right. So, that is what it is, and you remember we had calculated this as 25, this is the seed. Now, we can again do the same thing, we can drop it or we can just double click here and it should work. Just a minute. Usually double click here works. Excuse me. So, you can see that these are the states that are getting generated, right. So, notice that 25 got generated again here, okay. So, 257, right. The reason is I think we had one header row, right. So, it repeats after 255 cycles, right. We had this header row, remember. So, this is 25. Notice that 25 would only come here, right. So, let us mark this 25 and then let us see whether there is another 25 somewhere. If you want, we can make it even more specific. So, let us say this means J2 equals 25. Okay. Okay, sorry. So, J2 equals 25, that means which is true or false. Okay. So, now let us see if 25 occurs anywhere else. Okay, all false. Okay. So, notice that it occurs here again. So, let us mark this guy. Okay. And you can verify that it does not occur anywhere else. Okay. So, that shows that it really does not repeat before 255 clock cycles. That clear? It occurs here. Okay. So, this is what is a linear feedback shift register, and how does it help us? It helps us by generating random numbers. Okay. So, many times we require random test vectors, and the LFSR helps us in generating random test vectors. The only thing is these are not truly random. Okay. These are what we call as pseudo random, because if we know the seed value and if we know the polynomial, we can predict the entire sequence. Okay. It is not random anymore if we know the seed value and the polynomial, right. So, generation of true random signals is a little bit more difficult. You will have to depend on physical parameters like time, etc., to generate truly random signals. But if you want pseudo random outputs, you can do it this way. Okay. So, this is what a linear feedback shift register is. I think I had shown you the Wikipedia page, right, LFSR. So, this is the Wikipedia page. You will find the polynomials for quite a few situations. So, for 2 flip flops all the way up to 24, you can find it here. So, you will see that they have given you a reference if you are interested in larger ones, right. They have given some references here. Okay, I think if you go to the bottom, you will find some references here, right. There is one reference yeah. So, you can say the following table lists examples of maximal length feedback polynomials, or also known as primitive polynomials, up to 24. Okay. And the number of different primitive polynomials grows exponentially, right. There are a lot of primitive polynomials, right. So, this is a good reference. So, if you go there, you will find if you are ever requiring 64-bit, 128-bit, etc., you will find okay. The other important thing to note is, see, there are two types of LFSRs. Okay, the one which I showed you earlier is what is called as the Fibonacci LFSR. Okay, so it looks like the one which I just showed you. We have a shift register, and then we take the taps. Okay, these are called taps. Okay, in this case, the 11th output, 13th output, 14th and 16th outputs are being tapped, and we are XORing them, right. And we are connecting that value back to the main input, right. Whereas there is a alternate way to build LFSRs, and that is this guy, right. So, this is known as a Galois LFSR. So, the same LFSR has been shown in two places, one using the Fibonacci construction, and the other one is the 11, 13, 14 and 16, I believe 11, 13, 14, 16, it has been constructed like this here. Okay. So, the change is the XOR gate is now sitting in front of the D flip flop. Okay. If this is the D input and this is the Q output, you will see that the XOR gate is sort of sitting in front, right. The advantage of this kind of an LFSR over the Fibonacci LFSR, some people refer to this as type 1 and type 2 also. So, some people call this type 1 LFSR, okay, and some people call this one as type 2 LFSR. You can also call them Fibonacci and Galois LFSR. So, the advantage, as you can see in this Galois LFSR, is you can build a cell. Okay, you can build a standard cell where we have an LFSR preceded by the XOR gate, okay, and that can be used in these places. So, we will need 4 such cells, okay, I am sorry, 3 such cells, 1, 2 and 3, and the remaining are the ordinary D flip flops. Okay. So, whereas in the other case, okay, of the Fibonacci LFSR, we will need 16 D flip flops, okay, but we will need XOR gates which are separate, okay. And from a layout perspective, you will possibly appreciate that the Fibonacci LFSR which you are seeing here may be little bit more difficult than doing the Galva LFSR. The Galva LFSR will have a sort of a regular layout. Okay, we can have 2 types of cells, and we can just place them side by side and make near neighbor connections. Whereas here, some wires have to be routed all the way from 11, etc., etc. Whereas you can see here that only near neighbor except the last one. Okay, there is only one wire that is going all the way from here to here. Okay. So, other than that, this may be much more regular and more amenable to VLSI layout. Okay. So, I will encourage you to sort of build another example, maybe take the example of maybe 9-bit or 10-bit, right, and convince yourself that these LFSRs sort of do a great job of pseudo random test pattern generation, right. So, I hope the idea of Fibonacci and right. So, please understand the importance of Fibonacci and Galva LFSRs. Okay. The other thing that you must understand in the example of the LFSR is when we simulated it, right, you will find that there is a lot of correlation between the adjacent bits of the LFSR, right. Let us say we were doing the example of let us do an example of a 3-bit one, which we possibly did earlier also, right. Let me do the example of a 3-bit LFSR. So, 1 x square x cube. There will be at least two primitive polynomials. One is x cube plus x square plus 1, and the other is 1 plus, so this is 1 plus x square plus x cube. The other one will be 1 plus x cube. So, you can verify that they both work. Okay. So, if you start with 0 0 1 as the test seed of the LFSR, then the next cycle will be 1 0 0. Okay. Then it will be 0 1 0. Okay. And then it will be 1 0 1. Okay. And then 1 1 0. Okay. And then 1 1 1. Okay. And then 0 1 1. Okay. And lastly 0 0 1. Okay. So, you can see there is a sort of a correlation between these two signals. Okay. One of them is simply the value which is shifted. Okay. So, this may not be desirable in some situations. Okay. We may not want the outputs to be like that, right. So, sometimes people add what are called as phase shifters. Okay. So, what you can do is, if these are the outputs of the LFSR, okay, this is a 3-bit LFSR. You can take, we can add what is called as a phase shifter. So, this output could be the XOR of let us say these 2 bits, and similarly this one could be the XOR of these 2 bits, okay, and this one could be the XOR of these 2 bits. Okay. So, we could try adding such a phase shifter, and the output of the phase shifter will have less correlation between the adjacent outputs of the LFSR. Okay. So, this is what a phase shifter is, right. So, let me show you a phase shifter example maybe in the Wikipedia, right. So, phase shifter in LFSR. Okay. So, images, okay, let me see, here is it is explained here, right. So, the LFSR generates random pseudo random sequences, and the phase shifter is added in front of it. So, let me see if I can see a diagram here. Yeah, this is a, here is one phase shifter. Okay. So, the LFSR outputs are being taken, and in this example the XOR of these 2 is being provided as one of the outputs of the phase shifter. The XOR of these 2 bits is being given as one of the inputs of phase shifter, etc. Okay. So, in this example they took a few phase shifters, in maybe 3 in this example, but it could be any number, right. It is basically used to reduce the correlation, okay, so that the outputs appear to be uncorrelated to one another. That is a good property of a random sequence, right. So, maybe we can go back to this guy here, right. So, if you wanted to generate the phase shifter output, then what you have to do is you have to pick some XOR gates. So, maybe we decide to XOR X this guy X1, maybe we should call this X1 here. Okay. So, X1 and let us say X3 are being phase shifted. So, we can say XOR of I think XOR is allowed, XOR of A2 and C2. Okay. So, if you do not want this false to appear, you can try adding a 0 or something like that. Okay. That will make this 0. Okay. So, sort of a trick, right. So, here I have taken A2 and C2. Here you can take maybe B2 and D2. Right, and so on. Okay. So, these will be the phase shifter outputs. So, I may have 8 such terms. Okay. Maybe this we decide to do as it is. Okay. This is nothing but C2. Okay. So, we took A2 XORed with C2, B2 XORed with D2, C2 is as it is. Then this may be XOR of D2 and F2. Okay. Okay. and so on. So you can pick the outputs, and let us complete it. So A, B, C, D, E2, and let us say H2 plus 0. That 0 is just to make sure that the number does not appear as true, false, but appears as an integer. Then I think this is XOR of F2 and maybe C2, okay. Then plus 0. Then G2 and E2, okay. And then XOR of H2 and maybe G2 plus 3. Okay. So once we have done this, this is a phase shifter output P1, P2, P3, P4, P5, P6, P7, and P8, and actually we can generate P9, P10, etc. also by XORing other pairs. See, when we have 8 numbers, if we consider them in pairs also, we will have something like 8C2, right? That is approximately 28, I think. 8C2 is, I think, 8 times 7 divided by 2, that is 28 possibilities. So strictly speaking, we can generate 28 terms here, okay. So feel free to generate other terms, right? And then if you do the same thing, extend this guy, you will realize that the outputs are little bit quite random, okay. So we could try feeding this. In fact, we can generate more terms, P9, P10, P11, etc. And those can be used as pseudo random pattern generators, right. So that is what a phase shifter is all about, okay. So let me just write that down. So we could take the outputs of this shift register, just remove this guy here. So we had a 3-bit LFSR. So we could take the outputs. Let us call this as x1, x2, x3 if you want. We could take x1 and x2. We could take x2 and x3. And we could take x3 and x1. Okay. So this could be one way to construct an LFSR. I am sorry, phase shifter. Another phase shifter could be this could be a 3-bit LFSR. So we can take x1, x2, x3, and this x1 we let us say we take as it is, x2 we take as the XOR of these two guys, and x2 and x3 we take it here, right, and this x3 comes as it is. So we can have more outputs also, okay. So that is the reason why sometimes they write LFSR followed by phase shifter is shown like this. and this can go to a circuit which we want to test, circuit under test. Okay. So, we will initialize the LFSR to the seed value, and then we will keep applying clock cycles to the LFSR, and then as it cycles through all the states, the phase shifter outputs will be somewhat random, right, and the circuit under test will produce responses to these random test vectors, right. But what do we do with them? So, that is our next question, right. Remember what we are trying to do.